All right, so I wanted to talk briefly about how eigenvectors are going to come back in for the solution techniques of these matrix differential equations that we're going to be seeing. So things that look like this form and maybe also with this tacked on in addition to it. But let's just concentrate on this one for right now. So the idea is that rephrasing in or recasting our system in terms of matrices, this facilitates the use of eigen techniques. And so this is why we learned about eigenvalues previously. And so let's take an example or how and see how this works. So we will consider the system x1 prime equals 4x1 minus 3x2 and x2 prime equals 6x1 minus 7x2. And so we can convert this then into the matrix system that looks like x prime equals 4 minus 3, 6 minus 7. All right, and so here is our matrix A, and we can solve this system using the eigenvalues and eigenvectors of A. Okay, so let's go ahead and find the eigendata. So the eigenvalues, for that we're going to be looking at determinant A minus lambda I, like we always do. And so this is going to be 4 minus lambda minus 3, 6 minus 7 minus lambda. And so we do the usual thing and multiply out the products, and we get lambda squared plus 3 lambda minus 28 plus 18. And so then that becomes lambda squared plus 3 lambda minus 10, which we can factor as lambda plus 5 lambda minus 2. So we end up with lambda equal to minus 5 and 2. Okay, so now we look for the corresponding eigenvectors. So let's see, so for 2, we take A minus lambda 1I, so we subtract 2 from the diagonal, and we have 2 minus 3, 6, and minus 9. And we row reduce this matrix, and we have 2 minus 3, and then if I subtract 3 copies of this row from the second row, I get my zeros. And I don't need to go all the way to reduced row echelon form to see that I can take an eigenvector 3, 2. That'll be orthogonal to the first row here, so that's good enough. And then I'm going to take eigenvalue minus 5 and subtract this one from the diagonal. And so I have, let's see here. So I'm going to get 9 minus 3, 6, and minus 2. There we go. Okay, and so then I can row reduce this one, and let's see, so I'll divide that first row by 3, and I get 3 minus 1, and the second row is a multiple of that, So I get v2 equal, and I'll take 1, 3. Okay, so let's see. So now I've found lambda 1 equal 2 and v1 equal 3, 2. And I also found lambda 2 equal to minus 5 and v2 equal to 1, 3. And so now the magic happens. And if I take my first solution to be e to the 2t 3, 2, or if you want, you can write it as 3e to the 2t 2e to the 2t, whichever you prefer. And so key point here, I'm taking the eigenvalue and putting it up here next to t, and then I'm just strapping that next to the eigenvector that I found. And I'll do the same thing over here. So I have e to the minus 5t times the minus 5 eigenvector. And so again, just for emphasis, I'm taking that eigenvalue and I'm putting it right here next to t. Okay, so the general idea is I'm assembling things like this: e to the lambda k times vk. Okay, so now let's check. And this will show why this magic trick works. So if we do a times x1, then let's see. So our a was 4 minus 3, 6 minus 7. And our x1 is e to the 2t 3, 2. Right? Okay, so from the point of view of matrix multiplication, this here is just a scalar, right? It's not a matrix, it's just a scalar. It's a scalar that depends on t, but that's fine. So I can pull it out in front, e to the 2t, because scalars are slippery. And the rest goes like that. And then I can evaluate this part. And I know that this guy here is an eigenvector. So it's going to end up just giving me the scalar multiple. So let's see. So this is the eigenvector for 2. So this is going to be like that. Okay. Meanwhile, if I do ddt applied to x1, then I'm doing ddt applied to e to the 2t 3, 2. And now from the point of view of the differential operator, we've got the it ignores the other part. This is just constants. And so it's going to be ddt e to the 2t, and we can pull the constants outside. They'll be whichever way they want to be. And so if we differentiate, we get 2e to the 2t 3, 2. And then key point, these guys are going to be equal. And so just in case this part here made you slightly queasy, let's do the long way. So remember, we can also write that vector as 3e to the 2t 2e to the 2t, like we had back in the beginning. And then the way you differentiate a matrix is you just differentiate every entry. And so it looks like this. And now you should have no discomfort about the idea of pulling out the constants. we evaluate the derivative, and then for the last step here, we have this this constant, which is common to all entries of the matrix. So it's the same thing as the scalar multiple of the matrix by that number. So I can pull it out in front. And then that gets us back to where we were before. So the moral of the story is that if A times VI is equal to lambda, here let's call it K, AVK equals lambda K VK, then X prime is going to be equal to XK prime is going to be equal to AXK, where we've done e to the lambda K TVK.